What did we impose before? We just said, hey, I have some vortex stuff going on. That's way over at the boundaries. Let's not worry about it too much. And just go, I'll use my FFT. Okay, fine. Now, we have something different, which is we have stuff in here. There's my wing. And I have boundary conditions on that interior of the wing. Okay, you're going to have to take that into account. First and foremost, I just put that in there, and you can't use Homework 4 code anymore. Homework 4 code was all about finite discretization. There's nothing in there. All I have to worry about is what's out here. Don't have to ever think about in there. That thing puts a giant hole in your domain. Your sines and cosines that you're using for spectral methods, they don't know what to do with this. The solution cannot exist in there. The flow field in there is non-existent. Yeah.
If your wing was a perfect box that fit the grid,
then you could take care of it. Yeah. So if you were to make this as your wing, then yes, you could in fact think about discretizing, and this would be pretty easy to handle under this. Then you could say, okay, I could probably fix up my Homework 4. Discretize right, I have a rectangular wing. I would not suggest flying on such a plane. If you see one out there, like, hey, those engineers, they probably really wanted to use their Homework 4 stuff, and they designed a plane with rectangular wings. I will fly that plane. Okay, that would be bad. But now if you have some generic wing structure, and typically complicated, we have to figure out what the boundary conditions are on that. So, all right, so it becomes a pretty hard problem, right? You have to now solve this set of equations here in that domain with that boundary problem sitting right in the middle. And how do you want to handle that? Okay, so I don't want to handle it as much as possible. So let's do some simplifications for a moment. Let's try to simplify as much as possible, and then we can come back up from there. So, steady state flow. Let's start with that. Let's assume so steady state flow is awesome. Here's why. I'm going to show you why. Ready? Here's your governing equations. Here's all your dynamics. So, steady state. What does that sound? What does that mean to you? Does it bring any connotation to your mind? Steady state? No time dependence. In other words, you say, okay, so basically all the transients have died off. I start up some flow field and it kind of settles down to what it wants to be. It's not changing in time. In fact, what ends up happening to this equation as you run it forward for a very long period of time? This is wave behavior. That's diffusion. Do you know what diffusion does to you as time goes to infinity and you got nothing else coming in? This will make your solution go to 0. In fact, you had all these simulations, right, in Homework 4. How long did you ever run out your simulations? Anybody throw out something? Hundreds of units? Anybody running out hundreds of units? Okay, you still see stuff there. Try running. I don't want you to necessarily try this, but if you just kept running it out, you'd find that everything would just go to 0. This is why we picked this parameter to be like that. Okay? Because this diffusion term kills everything. And at least in this system, we don't have any forcing. Forcing could add energy back in the system, but we don't have that. So eventually, steady state flow means vorticity is going to go to 0. Okay? So, That equation's gone. Okay? And what do I got left? This equal to 0. How hard can that be? See why we like steady state flow? Look how nice that is. Okay? Turns out that's kind of hard too. All right? So first we want to understand this. So our technique here is going to be the following. We're going to solve the simplest problem in order to figure out how to handle boundaries. That's where you start, right? If you don't know how to solve this problem with complicated boundary, you're never going to solve that. Okay, we'll start with that philosophy first. So don't start this until you can take baby steps there, okay? Baby steps first, here, then we'll go from there. All right. So I've greatly reduced our problem. There it is, pretty simple. And so now what we want to do is start saying, okay, I have the dynamics I want to solve now, so we can come back here and say, great, steady state flow. All I got to do is solve that in this region. And then now let's talk about boundaries. Because all I have to worry about is the stream function now. Now, what are my boundary conditions? Well, presumably, my fluid is coming in like this. Right? And this is coming in from the x direction, right? So this thing here would be, let's call it u is equal to u naught. I have some steady state flow coming in here. Now, if it's steady state flow, when I get back out at the other end, it once again should be as if nothing had happened. Okay? Goes around this thing, does what it's going to do, comes out looking like that. Okay? So those are fairly simple boundaries. Now what about the top and the bottom? Same kind of thing will happen, which is one of the things you want to think about, and you can actually see this in the cylinder. If I have a cylinder, if I go far enough away, although the field is deformed around it, as I get up here, it's as if nothing had happened up here. If I'm far enough away from this object, far enough up, the flow is just straight across. Okay? So that's like moving my boundary out towards infinity. Remember, we're not going to really do anything at infinity. We're just going to say, go up far where treating it like infinity seems reasonable. Does that make sense? Okay? So another way to think about this is, I don't want any flow field across there. Okay? So here's what I've represented in terms of velocities. So in other words, over here, I want, remember what the flow field is? The velocity in the z direction is 0. We do something like that. All right. What does this mean for our problem? We're solving for psi. What is psi? It's our stream function. And I didn't actually write it down, did I? But here it is. Let me tell you what it is. The stream function is defined as the following. Those are the relations. This is how I define the stream function in the first place, which is, remember, when you define a stream function, it's the derivative of the stream function that matters. Okay? If you take the derivative of the stream function in different directions, it gives you back your flow field. Okay? So we solve for vorticity and stream function versus the velocity of the fluid directly. Certainly that's what we did in homework 4. All right, so what does this imply for us? Yes? Yeah.
Do we have the du dx equals to 0 on the top and bottom boundary? Like no velocity change?
Here we're looking at the normal, right?
Oh,
So that's
normal is
dc.
zero.
Yeah? Yeah, exactly. So we're going to try to apply normal across the top and the bottom to be 0. And remember that W is the velocity of the fluid across the normal. Because the normal now,
No, I know that's true, but you don't care about like no friction on the boundary.
yeah, we're not going to assume any kind of friction or anything there. In fact, these are far away. What we are going to worry about things like this, boundary effects, is right here on that wing. So here, the flow field, we're just approximating what it would look like far away. There are no real boundaries actually out there, right? It just, I have fluid coming in, fluid coming out, should be parallel. Here, we're going to have to impose something like no slip boundary conditions.